Hi everyone, and welcome to the second video on the series about number theory. In this video, we'll be looking at discrete valuations on fields and discrete valuation rings which arise from those. The motivation of this is that discrete valuation rings are kinds of rings that are some of the nicest behaved and will be relatively easy to work with in the context of not just number theory, which of course they play a very important role in, but of rings in general. So we start with this first definition of what it means to have a valuation on a field. It's a group homomorphism, so it satisfies the usual v of x times y equals v of x, v of y, from the multiplicative group of the field to the real numbers, such that for all x, y in the field, we have v of x plus y greater than or equal to the minimum of the valuations of x and y, respectively. This is somewhat dual, in fact, to how we saw absolute values defined in a field, and we'll see the relation in a little bit. So we can, first of all, extend any valuation to a map on not just the multiplicative group, the non-zero elements of the field, but to the field itself in full generality, to the extended real numbers, where you adjoin this infinity that's said to be greater than any real number, by setting the valuation of 0 to be equal to positive infinity. Now we see where the connection to absolute values come in. For any constant between 0 and 1 strictly, we can define the absolute valuation with respect to some valuation v, where you resolve this to be equal to c to the power of negative v of x. And when we looked at, for example, the p-adic absolute value, we took c to be something convenient like just 1 over p. So this yields a non-Archimedean absolute value, and we can sketch the axioms out really quickly here. So clearly we have this definiteness property holds, where the absolute value has to be 0 if and only if you're considering the 0 element. It's multiplicative as follows. You can just combine the exponents into this, and this is just as we have it over here. And finally, we have the non-Archimedean property. In fact, we can just do this directly without even showing the third usual axiom, because remember, non-Archimedean inequality is strictly stronger than the third axiom we usually use for an absolute value. So the image of V and R is what's known as the value group of V. Now, if V has its value group or its image in the reals equal to the integers under addition, notice, actually, I should clarify this up here, that this is written additively. So it's a discrete valuation if its image in the reals is the integers. Let's note that any discrete subgroup of the reals is isomorphic to z, which means that it's either z or it's some multiple of z, so nz. And we can just rescale the valuation with discrete value group such that we can make any valuation with discrete value group a proper discrete valuation. We define now the valuation ring associated to discrete valuation, or valuation in general. And this is denoted by A. It consists of all elements in the field whose valuation is non-negative. And coming off of this, we define a discrete evaluation ring, or DVR, the central focus of this video, to be a domain. Sometimes this is referred to as integral domain. I like to call it just domain. And in both cases, it just means that the ring has no zero divisors, which means that x times y equals 0 implies that x or y equals 0, if not both. It's a domain that is the valuation ring of its field of fractions, right, with respect to some discrete valuation. So we'll unpack this by looking at some examples later and some other properties that these hold, because this is certainly not the only characterization of DVRs. In fact, far from it. We note really quickly that a DVR can never be a field because we have the image of the fraction field of A under the valuation, which is equal to z by hypothesis. This is not equal to the non-negative integers, which would be the image of A under V. Okay. Although they're not fields, though, the idea is going to be that discrete valuation rings are the closest we can get to fields without being fields themselves. Hence, they share very, very nice properties with fields, just being short of them. So let's recall this definition of the valuation ring we looked at in the previous page of a field with respect to a valuation V. defined as the ring A, so that all elements in K with non-negative valuation of V. Here we see that every valuation ring is in fact a domain. If X and Y are non-zero elements, we want to show that their product is itself non-zero. To this end, we consider the valuation of their product, which is the sum of their valuations. This is by hypothesis. This is not equal to infinity because X and Y are non-zero. If one of them were, then this would not be true, which implies that xy cannot be equal to 0, otherwise we would not have v of xy not equal to infinity. Right? If it were 0, then we would have this equality hold. And also notice that every valuation ring has its fraction field to be k, which is the field that we started with initially. So we can pass back and forth by taking the valuation ring considering all elements of non-negative valuation and go back by taking the field of fractions of its valuation ring to get k. So now we look at, for any element x that's non-zero, or equivalently in the multiplicative group of the field, v of 1 over x, so the multiplicative inverse, is equal to v of 1 minus v of x. We quickly note that v of 1 equals 0. This can be checked immediately. So this is just 0 minus v of x, which equals v of x. Hence, at least one of x or its multiplicative inverse has non-negative valuation, equivalently lies in A. This means that x is in the group of units of A if and only if it has 0 valuation. This is because if it's like non-zero, let's say, if it's positive, then its multiplicative inverse will have a negative valuation, and only one of them is going to lie in A, right? Its inverse will not. And conversely, if it has negative valuation, it won't lie in A itself. That's out of the picture, but its inverse, in fact, will have positive valuation and will lie in the units. So the only way for this to be possible is if we have 0 equals negative 0, right? So the number has to be equal to its additive inverse. So v of x has to be equal to 0 to be a necessary and sufficient condition to be a unit in A. We look at this unit group, and we note it down and characterize it as the group of all x and k whose valuation is 0. So going off of this idea, we can in fact partition the elements of k star by the sign of their valuation, whether it's equal to 0, positive, or negative. We just remarked if it's equal to 0, this is equivalent to stating that it's a unit in A. If it's strictly positive, it is an A, but it's going to be a non-unit, so A disallowing the units. And if it's less than 0, it's not even going to be an A at all, but its multiplicative inverse will be, which we write as 1 over x, and that, since it's going to have positive valuation, you switch the sign, this is going to be in the non-units of A. Great. Looking at this idea of partitioning the elements of k star by sign of their valuation leads to actually a more general but equivalent notion of a valuation ring, where we say that a valuation ring is any domain A with some fraction field k, which has the following property. For any element x in the field, either x is an A or x inverse is an A. And this is one of the rare times in mathematics that this is actually the exclusive or. So it's one or the other that happen, unless, in fact, x equals 0. So I should actually qualify this as exclusive or if and only if we have x and k star. In general, it's fine if we have both because x can just be with 0 valuation, but this is the definition now. As I've written it here, it's inclusive if it's just x and k in general. Either x is in the valuation ring, or sorry, here it's either in the domain or the inverse is in the domain with respect to the fraction field. Great. I've rewritten this definition up here. A valuation ring is a domain with field of fractions k, so that for any element in the field, either it lies in the valuation ring or its inverse does. Suppose that a domain now, this is the case we're going to be interested, a domain A is the valuation ring of its fraction field with respect to a discrete valuation V. We characterize those elements in A for which they have valuation equal to 1. So if V of pi equals 1, we call pi a uniformizer. These exist because we note that quickly the image of the valuation ring under V is just the non-negative integers. So because of that surjectivity, we have some element in here such that the fiber of 1 is equal to, let's say, pi, where pi has valuation 1. We fix such pi uniformizer such that we have this following realization where we can write any element that is non-zero in K as the product of a unit and some power of a uniformizer, where u is going to be, sorry, this is n, so n is the exponent. I write my u's and n's somewhat similar. This is n, which is equal to the valuation of x, and u is simply x over pi to the n, which is some unit that's actually unique, so it's uniquely determined, and this entire expression is unique. This shows that the structure of DVRs is already very simple, because basically once we fix a uniformizer, which we'll see is unique up to a unit as well, we can describe every element as the product of a unit, which is uniquely determined in and of itself, and it you take the product with some power of the uniformizer. Because of exactly what I've just said, that we can always break apart elements uniquely as such, every discrete valuation ring, or valuation ring in general, is a UFD, unique factorization domain. More can be said. In fact, it's a PID, so a principal ideal domain. Note the classic equivalence, the classic implication, PID implies UFD. If you have a principal ideal domain, you're automatically getting unique factorization of your elements. So to show it's a PID, we note that every non-zero ideal in A is of the form something generated, let's say by pi to the n, which denotes all elements in A whose valuation is greater than or equal to n. So this is going to be every form of every ideal as n varies. Note that this ideal depends only on n and not pi, because for any other uniformizer, let's say pi prime can be uniquely written as u times pi, so any pair of uniformizers differs only by a unit. So this is even simpler structure than we started with. So by looking at these pi of n ideals, we note that as n varies across the non-negative integers, that they form a chain, or I should properly say totally ordered set, so they're ordered by inclusion. And the maximal ideal is that for which the valuation will hold all the way down. So you can keep saying that this is included and v of a is greater than or equal to n minus 1, and that is included in v of a is greater than or equal to n minus 2, and so forth. The maximal ideal is called the one generated by pi, where it consists of all elements whose valuation is strictly positive. Now, this takes the elements that have strictly positive valuation, and we noted how we can separate the elements in a discrete valuation ring or valuation ring in general by the sign of their valuation. So we have this unique maximal ideal, in fact, and this turns A into a local ring with residue field A mod M. This is the terminology we use. Local just means it has unique maximal ideal. The residue field of a local ring is just the ring modulo its maximal ideal. Okay. So now we look at how to go from a discrete valuation ring to the respective discrete valuation. We go the other direction now, and we can get this passage both ways. So given some discrete valuation ring A with its unique maximal ideal M, we can define this function from the ring to the integers by sending every element of the ring to some n. This is the unique n such that everything generated by A, since we noted the form of every ideal, is the corresponding power of the maximal ideal, so of the form generated by pi to the n for uniformizer pi, and we also have, by convention, v of 0 equals infinity. Now that we've defined it on the ring, we can extend this to its field of fractions, so we can extend v to k by defining v of a over b equal v of a minus v of b. This affords a discrete valuation on the field k as a whole, and it's got the corresponding valuation ring A of all elements x and k, such that v of x has non-negative valuation. Note that the maximal ideal in this, as we remarked earlier, consists of those for which this is a strict inequality and not just a weak one, and the ones for which v of x equals 0 we will look at in a moment. Any discrete valuation v on k with valuation ring A has to satisfy v of pi equals 1, because the image of A is just the non-negative integers, otherwise this would not hold, right? So there exists some pi in the maximal ideal M, and we can basically give almost a coordinate-free description of a uniformizer. So without making reference to an explicit discrete valuation, v of pi equals 1 if and only if that pi generates the maximal ideal. So we get a correspondence or an equivalence between uniformizers as we defined them earlier, those for which the valuation equals 1, and generators for the maximal ideal. So it doesn't even matter which discrete valuation we pick, because in fact, no matter what, uniformizers, or those that generate the maximal ideal, will always have valuation 1, irrespective. So now that we've gone through this theory, we look to give two specific concrete examples that solidify our understanding of discrete valuations and rings. One goes directly to what we remarked in the first lecture, which is with the p-adic valuation. So this is, recall, v sub p from the rationals to what I like to denote as z sub infinity, the extended integers where you consider z adjoins some infinity. Sometimes I'll write this for r as well, extended real numbers, the complex numbers. Sometimes I use that for the Riemann sphere, so on. This has the valuation ring denoted as follows, which consists of all elements a over b, just rational numbers. Both of these are in the integer, so yeah, rational numbers as I said, and p does not divide b. For those familiar with their commutative algebra, this is the localization of the ring Z at the prime ideal p. We'll look at localization in greater detail in the next video because it's crucial to a lot of the ideas that we want to get solid. So this is the localization, and it's got maximal ideal just generated by p. This is typically true for localization, and what's also true is that it commutes with quotients in the sense that if we take the residue field, this is actually isomorphic to z mod pz, or just the finite field of p elements. So we get quite a simple description. For a second example, we look at, for any field k, a valuation that's afforded from the Laurent series to the extended integers, and you take some Laurent series as follows, where n naught is any integer. If it were positive, say, or non-negative, this would be just a power series. So this gives you n naught, where a sub n naught is not equal to 0, right? This gives you the order of vanishing for any function in the, let's say, some invertible function that is in the Laurent series. Then you can say v of f in z gives you the order of vanishing. Now this has a valuation ring associated to it, all power series in the variable t. Now, something we want to keep in mind as well is that for any element in the field, let's say alpha and k as I've denoted, we can also define a local discrete valuation. So local is sort of informally used here, so a discrete valuation about a point v sub a, which gives the order of vanishing of any f when expanded in Laurent series about the point a. And this is especially salient when you realize k to be a field like the complex numbers, or some Riemann surface even, fields of meromorphic functions on connected surfaces. And you can take orders of vanishing by looking at meromorphic functions there and looking where they vanish, defining their order as we classically do in complex analysis and the study of Riemann surfaces. That's one good example to keep in mind if you're familiar with that side of the theory. Okay, so this gives two nice examples to keep in mind. And for the last part of this video, I want to look at some equivalent characterizations of discrete valuation rings. So here they are in just 1 second. We're going to look at how many different ways there are to really look at DVRs and why they're actually so nice. They're sort of the second nicest kinds of rings beside fields. So we see that for a domain A, so that's just from the outset, it has no zero divisors. That's not a super stringent condition to have. The following turn out to be equivalent. We have A is a DVR, as we've defined it earlier. It's equivalent to having a Noetherian valuation ring, which is not a field. Now, there are 3 different ways, let's say, to define Noetherian. The main one is either every ideal is finitely generated, or it satisfies the ascending chain condition on ideals. Every inclusion chain of ideals that goes upwards eventually stabilizes. It is a local principal ideal domain that is not a field. So we noted local means that it just has one unique maximal ideal. PID, of course, is that every ideal is generated by one element. And we get something interesting here with a domain. Being a Noetherian valuation ring is equivalent to having the property of being a local PID when you're not a field. Also, we have the property, this is equivalent to being an integrally closed Noetherian local ring of dimension 1. Integral closure I'll get to in the next video with integrality in fully general sense. So I won't describe this in full detail, but we can reconcile it with what I talk about in the next video. Noetherian as above, local ring once again as above, and dimension 1 is something I mentioned in the first video of motivation, where it means that basically every prime ideal is maximal in this context. Okay, we get the fifth one here, that this is regular of dimension 1 and its Noetherian. Now, regular means that the dimension of the vector space of the maximal ideal modulo the maximal ideal squared over A mod M, so that is a field, the residue field. So M mod M squared has dimension equal to the dimension of A as a ring, this curl dimension up here. And this is a slightly strange condition, and it only begins to make sense in the light of algebraic geometry, at least in my experience. We don't want to worry too much about regularity here, but just know that this is another equivalent characterization. So it's a regular dimension 1 Noetherian ring, and it is also equivalently a Noetherian local ring with non-zero principal maximal ideal. So the maximal ideal is, first of all, non-zero, non-trivial. We don't want it to be a field. And it's principal in the sense that the maximal ideal is generated by one element. We identified these as the uniformizers. Local and Noetherian is something we've seen it recur a few times here. Finally, we can say that it's maximal as a ring, which means that there's no intermediate rings between A and its field of fractions. So it's like somehow the closest ring to the minimal field. And it has dimension 1 again. Especially this last characterization, at least to me, shows that DVRs want to be fields very badly, in the sense that they obstruct any other rings from getting in the way of the smallest field that contains them. So they can be embedded in the field of fractions, which is canonically the minimal field that you can embed a domain in. And it is the closest ring to that. So a lot of these point to the fact that DVRs are essentially fields but slightly weaker. So sometimes, in the non-commutative world, we have division rings, which work very nicely. The commutative analog of having really nice rings that aren't fields are just DVRs. And with unique factorization, ascending chain condition, finitely generated ideals, and so on, we have a lot of really nice things going on at the level of both elements and ideals of DVRs. So these will become of great importance in number theory, as we define them to be localizations of appropriate rings that we encounter, and they will appear on their own as well. So this will become more transparent, hopefully, in the following videos. For now, I hope you're convinced about how nice DVRs are. We'll continue to give examples. Thank you, and hope to see you in the next video.